point in running. Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists.
Hello and welcome to The Naked Scientists, the show where we bring you the latest breakthroughs in science, technology and medicine with me, James Titko. Today,
he was on the sofa surrounded by everything that he'd won in football. England caps, FA Cup winners medal, League Cup winners medal, but he remembered none of it. Everything football gave him, football took away.
we're going in depth on traumatic brain injuries, assessing the risks of repeat head knocks and where research efforts are currently being concentrated.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
In today's Naked Neuroscience Takeover, we're going to be looking at the 1 million people in the UK each year who come to the hospital with a head injury. What's particularly concerning is that what can seem like a relatively minor injury at first can cause some patients to deteriorate very quickly. Here's Dawn Astle, daughter of West Brom and England footballer Jeff Astle, who died in 2002, aged 59, from accumulated brain trauma likely sustained during his playing career.
When my dad was about 54, so 1997 time, we noticed that he was just acting a little bit strangely and I guess saying things that were odd. He couldn't remember my son's name when he was born. He asked whether his mum was still alive and my grandmother had died, blimey, some 16, 18 years before. And we didn't understand what was happening to him, really. And my mum was really worried. Mum said to him, please go and see Dr. Jeff. I'm worried about you. And he agreed. So Mum literally rung the local medical unit up and they did some tests with him there. The doctor said to my mum, I'm sorry, Lorraine, but I think Jeff's got early onset dementia. Mum was just absolutely devastated, as we all were. And so tests and scans followed and they basically said that Dad's frontal brain cells were dying and there was nothing anybody could do. From that day on, really, the disease took more of a hold as the weeks and months passed. He was incredibly restless still. He became aggressive at times and he was never like that. He was on the sofa surrounded by everything that he'd won in football. England caps, FA Cup winners medal, League Cup winners medal, but he remembered none of it. And I always say that, sort of looking back now, everything football gave him, football took away. And then the day he died, it was 19th of January 2002. And I remember that day as if it were yesterday. And to be honest, that day continues to haunt me every single day. And it was while we were eating this little birthday tea I'd put on, he started to cough and it was getting worse. And I remember my partner and my brother-in-law helped him to his feet, but then his legs gave away. We took him outside to sort of get some air, but this coughing just seemed to get worse and we were screaming at him, literally screaming for him to spit the food out. You could tell there was food there, but he wouldn't spit it out. We were trying to open his mouth to get this food out. We just couldn't do it. It was just horrendous. And then there was that realization as, oh my God, is he breathing? And I remember calling 999 and myself and my partner were giving him CPR and it was just the most horrendous thing. And yeah, and sadly Dad ended up choking to death. There was nothing any of us could have done to stop it, and believe me, God, believe me, we tried.
I can only imagine, how difficult. Thank you so much for sharing that. You mentioned it was the game he loved and lived for that eventually ended up taking his life. Is that something that was at the forefront of you and your family's minds after the diagnosis and as his condition got worse?
I don't know. I don't know whether it was at the forefront because, to be honest, James, we didn't really talk about it very much. I guess in the background, there was always that, I wonder if, could it be type of questions that we all had. Dad was, he didn't have many opinions on many things. My dad didn't, probably apart from football, cricket and horse racing, to be honest. But one thing that he really believed in and was quite passionate about was, believe it or not, organ donation. And Mum, when asked about donating Dad's brain after he passed away, she had no hesitation. I mean, I guess little did we know all those years ago how much his brain would reveal. And thank God we did.
What exactly was it that came to light after your dad had passed away and his brain was handed over to the doctors?
Mum had already had a phone call from somebody from the coroner's court saying that there was going to be an inquest into Dad's death. And it was during the inquest when the pathologist, Dr. Robson, he stood and described how badly damaged my dad's brain was. And it was something we weren't ready for and something that was very hard to listen to. And he found that there was considerable evidence of trauma to his brain, and it looked like the brain of a boxer's. But he said that the main candidate for this trauma, which apparently was right through the brain, right from front to back, left to right, was the heading of footballs. But it was the repeated heading, I think that was the key, that appeared to be the problem. And then, having listened to that, it was Her Majesty's Coroner, then Andrew Haig, actually said Mr. Astor's type of dementia is entirely consistent with heading footballs, and his occupational exposure has made at least a significant contribution to the disease which has caused his death.
It was given his position on the pitch, perhaps, right at the business end, where he was being asked to head the ball a lot, unknowingly putting himself at extra risk compared to some of his teammates.
Oh, definitely. I mean, we know now, our footballers are 5 times more likely to die with Alzheimer's disease than you and I, and they're 4 times more likely to die with motor neurone disease than you and I, and twice more likely to die with Parkinson's disease. But that data, which the field study uncovered, also showed us that a former professional footballer's length of playing career and player position is tied to higher neurodegenerative disease risk. So centre halves, 5 times more at risk again, centre forwards, nearly 4 times more at risk. So Dad was a centre forward and his professional career was, I think, about 17 years.
Thank you to Dawn Astle, daughter of West Brom and England footballer Jeff Astle, for sharing her dad's story with us. The challenges that need to be overcome to improve outcomes for the many patients who suffer brain injuries were discussed at a recent meeting of the International Neurotrauma Society here in Cambridge, which is looking to lead the global push for better TBI treatments. We're going to hear now from Professor of Neurosurgery at the University of Cambridge, Peter Hutchinson, who was there. He gave me an overview of traumatic brain injuries.
These injuries can be divided into 2 parts. They can be what we call focal, so that's like a blood clot, which is either between the skull and the membranes or the membranes of the brain, and big blood clots need urgent neurosurgery, an operation to remove them. The second type is what we call diffuse injury, where the brain is swollen and bruised within the confines of the skull. Now, if you bruise your knee or your elbow, for example, that will swell. It will then go down. The problem when the brain swells is that it's swelling and it's confined by the tight skull. So the consequence of that is the pressure will go up inside the head. And if the pressure goes up, the amount of blood going into the brain will reduce. Delivery of really important nutrients for the brain, glucose and the gas oxygen that we need to survive on, delivery is reduced. So there is cell death and swelling, which compounds the problem. So this vicious cycle of brain swelling in the tight skull, increased pressure, reduction in blood flow, reduction in oxygen, glucose, cell injury, further death and more swelling.
And it's a case of the bigger the impact to the head, the worse the injury.
Diffuse brain injury has a range of severity. The mildest is called mild traumatic brain injury, and the mildest variant of that is called concussion. So that is an injury that can occur with or without loss of consciousness. We don't fully understand what's happening to the brain, but this is usually a transient disturbance of brain function from a number of causes, to more severe diffuse injury through what we call mild, moderate, and the most severe is called diffuse axonal injury in pathological terms, and that's when there is quite severe injury to the structure of the brain, to the nerves and the supporting cells. that is associated with loss of consciousness, which can often be very prolonged, and these can be very challenging to treat.
It's alarming what you said there about the concussions on the more mild end of the spectrum not necessarily having any symptoms, us not being able to detect when they've happened.
As you say, so concussion may be so mild and transient that it may not even be picked up. You sometimes see that on the rugby field where somebody may or may not have a knock. They may be transiently dazed, but that can be quite a difficult diagnosis to make. Sometimes it is more obvious. There's a short period of loss of consciousness. Sometimes people have very few symptoms after a concussion, but classically patients do have a number of symptoms. These can be what we call physical, so headaches, visual disturbance, dizziness, impairment of balance. They can be what we call psychological or cognitive, so impairment of memory, impairment of concentration, thought processing and planning. And then quite challenging can be what we call the neuropsychiatric symptoms, changes in behaviour, the way we respond to others, and mood disturbance, particularly depression, can be quite a big problem for some of these patients.
What do we know about how neurodegenerative complications relate to traumatic brain injuries?
So this is quite a difficult topic and something that we don't fully understand. There is a concern that particularly after multiple concussive injuries or even one severe traumatic brain injury, following the acute stage, that there is an impact on the brain in the longer term. So the risk of getting what we call neurodegenerative disease, probably the most cited is some form of dementia, but there are other complications such as seizures or even Parkinson's disease. And there's quite a lot of work going on now to try and relate that initial insult to these problems in life. The challenge is, how do you do those studies? We can try and control people who've had brain injuries against the normal population and compare their brains. But in order to answer these questions accurately, we need to do what's called longitudinal studies, where we need to follow patients who've had a brain injury for many, many decades and those who haven't.
There are also genetic and lifestyle factors at play here. That's the difficulty with ensuring we're addressing the causation here rather than just a correlation.
Exactly. So just to break that down a little bit, the genetic makeup, our genes do influence our outcome from brain injury. There is a sort of protein, apolipoprotein E, and the type of this protein you have can influence on how well you recover from injury. But in the longer term, I think some of the consequences, particularly professional people who play high-level sport and then they suddenly stop playing it for whatever reason, maybe they've got another injury, has a profound effect on them because this is their well-being, this is their life. So whether that is a result of brain injuries or whether it's that dramatic change in lifestyle is something that we really need to try and get to the bottom of.
In that pursuit, do we have a good working hypothesis? I mean, people might be aware that dementia, Alzheimer's, it's because of this build-up of abnormal proteins in our brains. Do we have any guesses as to the mechanism from which traumatic brain injuries or even mild concussions lead to that?
Yeah. So there's a number of studies trying to address the pathology and the pathophysiology of the link between the initial trauma and the dispositions in the brain later, but I don't think it's something that we do fully understand. There probably is some population link between brain injury and these later problems, but of course, how do you relate that to each individual? And that's of course is the challenge, where you're trying to differentiate between population studies and what in effect is a case report for each individual patient.
Consultant neurosurgeon Peter Hutchinson there, outlining what we do know, but also some of the vast gaps in our knowledge of brain injuries. You're listening to The Naked Scientists with me, James Titko. So far today, we've heard about the different severities of brain injuries, how swelling of the brain following a trauma can lead to a dangerous increase in pressure, stopping the delivery of blood and thus important oxygen and nutrients to the brain, and how devastating this can be. We've also learned how much there is still left to learn about the association between mild traumatic brain injuries, concussions, and neurodegenerative conditions like dementia. But given we do see an association in this area, and with head knocks a common feature of many sports like football and rugby, attention has turned to how we can make them safer. Adele Helmy is an Associate Professor of Neurosurgery at the University of Cambridge.
So there's lots of important research going on about the burden of concussion in sports and thinking about how that might be reduced in a practical way. And the issue within changing the rules or dynamics of sport is getting the balance right. We don't want to take away the competitive element or the essence of the sporting endeavour in itself, but at the same time, having recognised that there may be these risks in the very long term, is to appropriately risk mitigate. And that's different for different sports. Probably the best example that people will have come across is the change in tackle height rules in rugby. We had a talk about that within the public session. And one of the things that came out within that talk is that the enormous resistance in the first instance to a new approach such as this, but the fact that in the longer term it's actually gains great traction because people have recognised that although it is a change to the way that the game is conducted, it may in the longer term accrue substantial benefit. Another example would be the change in heading rules, particularly for grassroots football. This was first taken up by the Scottish FA, but also the English Football Association from this year has introduced those new heading rules, and those will be filtered through at the different age groups such that in 3 years' time, no primary school children will be heading the ball. It does require a change to the sport. It does require engagement of parents, coaches and so on. But I think in the longer term, until we better understand the risks that are associated with these endeavours, it does make sense, particularly at grassroots, particularly for young people, that we try and minimise the risk of concussion in the longer term.
We heard about Jeff Astl's story earlier in the programme. I'm thinking of a BBC documentary where Alan Shearer, another prominent footballer, underwent an MRI scan to have a look at his brain. He must have headed the ball as much as anyone in his professional career. And the MRI scan showed, a very healthy brain. We don't really know enough yet about who is affected. And that's why people show this initial aversion to the rules being changed, maybe.
I think in different contexts that there are different reasons. It's not a simple problem. And you're absolutely right. The absolute risk is not that large. There's definitely an increased risk, but many people may not be affected by these conditions, and the other risk factors, whether they be genetic or some other aspect, are critical. And because we don't understand these, and we have to be upfront about that, it's very difficult for us to counsel people in a reliable or confident way.
We've been talking a lot about dangers associated with participating in contact sports. The huge raft of health benefits that have been proven again and again in study after study associated with doing sport and levels of physical activity shouldn't go amiss in our conversation.
Clearly, as scientists and doctors working in this field, we're very interested in the pathophysiology, how repeated concussions may injure the brain and lead to this increased risk in the very long term of conditions such as dementia. But it's really important that this is put in context. So we recognise that sport is an important part of British national life and that there are huge benefits that accrue from that to individuals in terms of team building, learning discipline, teaching our children how to win and lose in the right way. We shouldn't dismiss all of those things. And the difficulty that we have, particularly when we're talking to members of the public, is to balance those risks. What we don't know yet is how big is a risk to an individual. And clearly, a lot of the evidence has come from professional sports for very good reasons. Those are the people with the highest exposure to these things like concussions. But it's really important to recognise that for grassroots or amateur sport, both the dose, the number of concussions that you might be suffering, and also the magnitude, how bad those concussions are likely to be much reduced. And really, we need to look at this in much greater detail before we can give you an idea of the relative balance of risks.
To bridge this gap between the crucial research that people like you are doing and the public understanding, what can we do? I'm referring really to the event not so long ago here in Cambridge.
So we're very lucky to host one of the largest neurotrauma meetings that runs. It's something called the International Neurotrauma Symposium. It brings together both head and spine trauma. And it also brings together both basic scientists, those are people who work within universities, perhaps in model systems, looking at head injury, but also the doctors, like ourselves, who treat head injury in an active way. The conference covers absolutely every aspect of neurotrauma. That can be inflicted violence, it can be military trauma, it can be modelling biomechanics, It can be looking at blood biomarkers, can be looking at scans and imaging, can be looking at new trials. But we're very acutely aware that this research is not just for us. It's not an ivory tower within the university system, but it's really important that this has direct applicability to people's lives. And given the recent advances and the public perception and the media coverage of sports concussion and dementia risk in particular, we chose a number of speakers from a range of sports: football, rugby union, from Formula One, and also the Paralympic movement. And this is essential both to engage with the public and learn what the priorities are for them, to allow us to draw in funding and engagement from different charities, but also to shape the sort of research that we do.
That was Adele Helmy, who's also a consultant neurosurgeon at Addenbrooke's Hospital. Clearly, whatever changes to the rules of sports we make, we're not going to eliminate head injuries from happening altogether. That's why innovations from pitchside to ambulances to intensive care units are also needed to help avoid as many deaths and serious disabilities as possible. Alexis Joannides is a co-director of the Health Tech Research Centre at Addenbrooke's Hospital, which won £3 million of funding earlier this year from the National Institute of Health and Care Research to support the development of medical devices, diagnostics and digital technologies.
If you try to make a difference, you have to take a structured approach. There are different parts of the patient pathway that you could tackle. There's preventing the injury in the first place. There's stabilizing the patient on the scene and in their way into the emergency department. Then there's protecting the brain from further injury in the hours and days after an injury, and that happens usually in intensive care. And then there's a whole piece of work and effort around rehabilitation and making sure after an injury you recover back to normal life as far as possible.
A lot of different stages then. Let's zoom in on one particular part of the timeline as you've outlined it for us and how we're working to make an improvement there.
If we look at acute monitoring, so this is usually happening once the patient has come to the emergency department, they've been stabilized, then there is a very vulnerable period, a critical period that the patient will usually be in critical care or the intensive care unit for severe head injuries. And there your focus is making sure the brain doesn't sustain any extra damage from what has already happened. So historically, neurosurgeons and intensive care physicians focus on brain pressure and making sure that doesn't go over a certain level that affects blood flow to the brain. But there are also other parameters, such as how much oxygen is getting into the brain from the blood, and also the metabolic status of the brain in terms of respiration and general metabolism. What we've been championing for a number of years now is a concept called multimodality monitoring, which is where you can have different readouts of the brain, pressure, oxygen levels, chemistry and metabolic demand. So how do you tackle that? Well, the most important thing is to know what are your readouts in terms of sustaining further injury.
Could you just take me through why it's that combination of factors that is critical for medical professionals to have at their disposal during that time?
So if you have this combination of factors, that enables you to tailor your treatments with the patient, be that giving salt solution to reduce the pressure, increasing the amount of oxygen delivered in the ventilator. So in order to customize what you give, you need to measure it. Now, if you say, well, how do we do that? Well, again, there's a number of stages. First, you need a device that allows you to put a number of different probes or thin wires into the brain safely. And then you also need to be able to measure the data and analyze it to work out what best to do. So, for example, we've just completed a phase 2 trial on having an algorithm for optimizing the pressure that the brain should be at with an individual patient. We're also working on a sensor that allows the chemistry, the metabolism to be measured in real time, because historically this would be done as a readout with a 4-hour time lag. So now we have more up-to-date information. And then really the ultimate outcome is looking at how the patient does down the line, and this is something that you would start doing at the critical phase before you start looking at what difference you've done down the line.
Alexis Joannides, neurosurgeon and co-director of the Health Tech Research Centre at Addenbrooke's Hospital. And Alexis was mentioning there the many stages at which doctors are trying to improve their interventions to better serve their patients. And a crucial aspect moving forward will surely be better drug treatments and diagnostic tools. Professor David Menon is head of the Division of Anaesthesia at the University of Cambridge and the project lead of a £9.5 million research platform funded by the Medical Research Council, which is adding vital knowledge in this pursuit.
I've been involved in traumatic brain injury research for the last 30 plus years. Over this period, there have been multiple trials of pharmacological agents which have consumed probably a couple of $1 billion, thousands of patients and pharmaceutical companies' investment, which have all failed to show any benefit in terms of improving outcome. And the question is why that should happen, because the preclinical models of disease suggest that these drugs should be working. And trying to investigate it, we came to the conclusion that 3 or 4 problems that needed to be addressed. The first was when pharmaceutical companies and other investigators took the results from preclinical models in mouse and rat and took it to humans, the assumption was that whatever pathophysiology, whatever mechanisms were present in those experimental animals were going to be there in humans. And what's more, they were going to have the same time course, the same importance. The second failure that they had was they made the assumption that because the drug got into the brain in these experimental animals, it would happen in humans as well. And finally, the endpoints that they were using were ones that were relevant to humans as well. And it became patently obvious that this was not the case, that this direct translational route was not going to work. And what we needed to do was to have an intermediate step of what's been called over the years now experimental medicine, where we study what's happening to the disease process in humans. So that was the first part of it, trying to find drugs that did what they said on the tin, that they interfered with the processes of traumatic brain injury in a way that we expected.
What is your new initiative, TBI Reporter, bringing to the fold here?
Because brain injury is very variable, if you want to look at the effect of a drug, typically you have to study many hundreds, often 1,000 patients because of the variation in the injury severity and variation in outcome. But if you want to just look at what happens to a molecule that's responsible for inflammation, you can do that in smaller numbers, typically tens of patients. But instead of doing it in one center, TBI Reporter allows us to do that in 6, 8, 9, and eventually a maximum of 16 centers, again, doing small numbers of patients, but getting through the studies much more quickly than we would if we were just doing it in Cambridge, for example. And that's important because there are so many questions to answer. The second part of it is there's been, as I said, a lot of studies in traumatic brain injury, both observational where patients didn't get any specific drug, but also the past interventional studies where drugs or other interventions were trialed. The data were collected, we got the information, the papers were published, and then the information was never looked at again. Now, across all of these studies internationally, we calculated that there were over 100,000 patients. And bringing all of those together would provide the weight of numbers that would allow us to answer questions that were simply impossible to answer in any individual study.
So it was all sort of just sitting there, that information, waiting to just be assessed by neuroscience researchers like yourself and the network you've set up.
Correct. So, for example, by combining 2 studies, we got together 5,000 patients and understood the genetic contribution to outcome from brain injury. And the bottom line is we found that about 25% of the variance in outcome is genetically driven. The card you're dealt with when you're born, genetic cards that is, have a huge bearing on how well or badly you do after the same sort of injury, but varying across patients.
You mentioned biomarkers. I wonder if you could just paint the picture of the diagnostic scene in traumatic brain injury.
So we are familiar with biomarkers in the setting of heart disease or cancers. And heart disease, if you come in with a chest pain, people will do a blood test to look at a protein called troponin, which is released by injured heart muscle. And that's now so well established that it's a key diagnostic tenet to diagnose whether someone's had a heart attack or not. Now, with traumatic brain injury, it's been very crude. So far, we've classified traumatic brain injury as mild, moderate, or severe, which is ridiculous. If you went and asked a cancer patient whether they had mild, moderate, or severe cancer, you'd get laughed out of court. What we need to do is to understand the precision diagnosis and apply precision medicine to these patients. Classically, We've used CAT scans to diagnose whether there is injury to the brain. But biomarkers are turning out to be very sensitive, perhaps even more sensitive than CAT scans. And the protein biomarkers we're talking about are proteins like GFAP or UCHL1. These are now approved for use to diagnose traumatic brain injury. The second is that it's important for prognosis. If you add in these protein biomarkers and look at their magnitude and the trajectory of appearance and resolution, they typically add between 10 and 15% to our precision of saying how well people are going to do. But the third, and perhaps the most important in the context we've been talking about, is to identify which treatments to attach to which patients. If we want to talk about what the body is doing in response to the injury, then understanding which inflammatory mediators and molecules are upregulated or increased in the blood and how these affect the ongoing process is very important. And using drugs that have been used, for example, in COVID, high dose of steroids or drugs that modify the inflammatory response would be very effective in patients, perhaps, who had a very excessive inflammatory response, but might only have detrimental effects in people who didn't have much inflammation to start with. And we're starting to employ that in clinical trials.
A promising note to end on. Thanks to David Menon, Professor of Anaesthesia at the University of Cambridge, and to all our guests who spoke to me on this topic. It feels like we're on the precipice of a significant period of progress in our understanding of brain injuries, owing to the tenacity of neuroscientists and doctors in the field, and the bravery of people like Dawn Astle, who have campaigned for years for greater awareness of the dangers of concussion, which have no doubt played their part in ensuring the vast sums rightly being allocated to the research projects we've featured today came to be. I hope I'm right, and that we start to see better outcomes for more patients as soon as possible. If you like this programme, you can hear more podcasts from me dedicated to our brains and nervous systems by subscribing to Naked Neuroscience wherever you get your podcasts. Or if the fascinating science of our genes is more up your street, then you can look for Naked Genetics, where Will Tingle will be there to take you through his adventures looking into the amazing variation in the natural world. But for now, it's time for me to tell you that The Naked Scientists comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm James Titko, and from everyone here at The Naked Scientists, thanks for listening, and until next time, goodbye.